Hello, this is Mr. Collier, and today we're going to do some proofs by induction. So there's basically three steps to proof by induction. First, you show that it's true for n equals 1 or some other initial n, the starting point. Then assume that it's true for n equals k, and then show it's true for n equals k plus 1. So I'm going to use this method to do some proofs. First one, we're going to prove that n cubed plus 2n is always divisible by 3. So you start off with your initial case for n equals 1. So we're going to prove it for n equals 1, or just show that it's true for n equals 1. So if n equals 1, we have 1 cubed plus 2n, or 2 times 1, which equals 1 plus 2, which equals 3. So obviously this is divisible by 3, so therefore it's true for n equals 1. Next, we assume it's true for n equals some integer k that's greater than or equal to 1. Okay? So I'm going to assume it's true for n equals k. That means that k cubed plus 2k is going to be a multiple of 3, and we can write that as, let's say, 3t, where t is some integer. Okay, so t is some random integer. And last step, we're going to show it's true for n equals k plus 1. Okay, so we're going to start off by letting n equals k plus 1. That means we're going to have k plus 1 cubed plus 2k, or 2k plus 1. So here we can factor out the k plus 1. Factor out k plus 1 to make it a little bit easier, I think. And then we're going to have k plus 1 squared plus 2. And work that out. We have k plus 1 times k squared plus 2k plus 1 plus that 2 there, which is k squared plus 2k plus 3. Next, we can expand the brackets. K times k squared is k cubed plus 2k squared plus 3k plus k squared plus 2k plus 3. Simplify again, we have k cubed plus 3k plus 3k squared plus 5k plus 3. Now if we go back and look at what we have for our assumption, we assume that k cubed plus 2k, hang on a second, we assume that k cubed plus 2k equals 3t. Okay, so we assume that k cubed plus 2k equals 3t, and we can, if we had k cubed plus 2k in our expression here, we could substitute that in. We don't have that, but we do have a 5k, so we're going to split that 5k into 3k and 2k, and then we'll be able to make a substitution. So let me keep that on green. So I'm just going to rewrite this as k cubed. I'm going to rewrite this as k cubed plus, and instead of 5k, I'm going to have 3k plus 2k, and then the rest is 3k squared plus 3. We saw previously that this is equal to 3t, so we have 3t plus 2k plus 3k squared plus 3. Oops, this is backwards. This should be 2k and this should be 3k. This equals 3t and this is 3k. And if you look at this, this is quite obviously divisible by 3. We can rewrite it in one more step by factoring out the 3. It's equal to 3 times 2 plus k squared plus 1. So this number is divisible by 3. So therefore, by induction, by induction, n cubed plus 2n is divisible by 3 for all n greater than or equal to 1. So we've proved this by induction. Let's take a look at another example. We're going to prove that this expression is divisible by 3. So we start off with our initial condition is n equals 1, and let's show this is divisible by 3. We have 10 to the power of 1 plus 1 plus 10 to the power of 1 plus 1, which equals 111, which is divisible by 3. So therefore it's true for n equals 1. Now we're going to assume it's true for n equals k, which is a number greater than or equal to 1. Okay, so that means we're going to have 10 to the power of k plus 1 plus 10 to the power of k plus 1 is divisible by 3, so we can write that as 3t for some t that is an integer. And lastly, we're going to show that it's true for n equals k plus 1. Okay, so we're going to use k plus 1 this time. We're going to have 10 to the power of k plus 1, which is k plus 2, plus 10 to the power of k plus 1, plus 1. So we're going to show that that's divisible by 3, and we want to make it kind of look like this up here. So what we can do actually is factor out 10 from each of these terms. So we can have 10 to the power of 1 times 10 to the power of k plus 1. That gives you 10 to the power of k plus 2. And this is 10 to the power of 1 times 10 to the power of k plus, or just k, pardon. Okay, so now it's looking a little bit like our assumption. So we should be able to make a substitution sooner or later. Okay, but what we have here in our assumption is we have 10k plus 1 plus 10 to the power of k plus 1. So if we want just this part, we're going to have to solve by subtracting 1 from both sides. So let me just write that down over here because I don't have room up there. So basically 10 to the power of k plus 1 plus 10 to the power of k equals 3t minus 1. Okay, so we're going to make that substitution in a second. So basically over here we have, and we can factor out 10 from these two terms. We have 10 times 10 to the power of k plus 1 plus 10 to the power of k plus 1. And this here in the brackets is exactly this. So we can substitute in 3t minus 1 here. We have 10 times 3t minus 1 plus 1. And we'll multiply that out. We'll have, 30t minus 10 plus 1, which equals 30t minus 9, which is 3 outside of 10t minus 3. So obviously this is divisible by 3. So therefore, let's just write it here, therefore 10 to the power of n plus 1 plus 10 to the power of n plus 1 is divisible by 3 for all n greater than or equal to 1, where n is an integer. Okay, let's take a look at one more of these divisibility examples. N equals 1, so let's show that's true for n equals 1. So we have a to the power of 1 minus b to the power of 1. That does equal a minus b, which is obviously divisible by a minus b. So therefore it's true for n equals 1. Then we're going to assume it's true for n equals k, which is some integer greater than or equal to 1. So a to the power of k minus b to the power of k equals basically some number t times a minus b, where t is simply some integer. Okay, that's how we show that's divisible by a minus b algebraically. And now we're going to show it's true for n equals k plus 1. Okay, so we're going to use k plus 1 now, a to the power of k plus 1 minus b to the power of k plus 1. And we should here factor out an a and a b to make it look more like our assumption. So we have a to the power of 1, or just a times a to the power of k, minus b times b to the power of k. Now what do we need to do with our assumption is we should probably solve for a to the power of k and then substitute it into our expression over here. So let me do that right here. So we're going to have a to the power of k equals, now on this side of the equation we have t times a minus b, so that's at minus bt, and add the b to the power of k, and that's what we have here. And we're going to substitute that in for a to the power of k. So we're going to have a times at minus bt plus b to the power of k minus b times b to the power of k. And next, I'm going to multiply this out. We're going to get a squared t minus abt plus ab to the power of k minus b times b to the power of k. And we can factor here by grouping. So the first two terms we can factor out at. So I have at times a minus b plus b to the power of k times a minus b. So that's going to be equal to at plus b to the power of k times a minus b. So since a minus b is a factor here, this is also divisible by a minus b. So therefore, any binomial a squared minus b, a to the power of n minus b to the power of n is going to be divisible by a minus b for all n greater than or equal to 1.